So hello everyone, my name is Yingfei, and currently I want to present our work on CVPR 2023, the 3D GAN Inversion with facial symmetry prior. Our team are from the Tsinghua University, Tencent AI Lab, Hong Kong University of Science and Technology, University of Cambridge, and Ant Group. Well, currently, we want to solve a problem of 3D GAN inversion, and there exist several works in 2D GAN inversion. They want to reconstruct a target human object in a pre-trained 2D generators. The 2D modeling solutions are limited by representational capabilities and are prone to inconsistencies when the viewpoint changes significantly. Therefore, we turn to the 3D generators. There exist several works that incorporate the 3D neural renderings modules into the generated models, which allows for the synthesis of free views. So we can see the video that it can synthesize 3D rendering results. Okay, so our goal is want to achieve the 3D GAN inversion, which means we want to reconstruct a monocular image in the 3D GAN generator. However, there exist several challenges to solve. First, with only a single monocular image and a lack of geometric information, the geometry of the reconstructed object tends to collapse into a flat surface. When fitting the side face texture, it will be even worse. We can see the video here. With the collapsed geometry, the texture will be even worse, and we cannot see correct texture in the normal views. And another challenge is that, as there is only a single view information, the lack of texture for the new view image tends to be blurred. And intuitively, we can construct the pseudos of the new views to constrain the geometry and the texture. To solve the above two challenges, we design a two-stage optimization strategy. Similar to PTI, we will first optimize a latent code W to obtain a rough geometry and texture. And later, we will further fine-tune the parameters of the 3D GAN to further overfitting the target texture. Okay, so in the first stage, we will optimize the latent code W+ of the 3D GAN. Intuitively, we can figure out that the human face is a nearly perfect symmetric object. Therefore, we can directly use mirroring process to generate a pseudos. The mirror view, along with the source view, can construct two views. The geometric constraints on the introduction of additional perspectives through mirroring can significantly restrain the geometric degradation. However, the human face is not a perfect symmetric object, and therefore we should incorporate more information from the source view instead of from mirror view. We design an adaptive weighting strategy to ensure a balanced reconstruction dependent on original image information and the mirroring. And specifically, we use a Gaussian noise function independent of the input yaw angle. Well, after obtaining the fine-tuned W+ latent, we can achieve a roughly corrected geometry and the texture. However, there still exists a distance between the current texture and the ground truth. Therefore, we need to further fine-tune the 3D GAN parameters to fulfill the process. In the second stage, we will fine-tune the 3D GAN parameters. At this time, we will further incorporate more pseudos to improve the texture's fidelity. We will use the depth-based 3D warping to construct new perspectives pseudos. We can project the pixels points from the source views onto the face objects. And then we can use the 3D point cloud to project onto new views. These pseudos, along with the source view and the mirror view, will be used to optimize the 3D GAN parameters. Still, the obtained pseudos have artifacts, and we should incorporate the useful information from these pseudos. We will use the authentic mask, sparse constraints, and depth regularization to ensure the correctness of these pseudos. In detail, we cannot use the uncorrect background information from the pseudos. Therefore, we only use the face region part information and we calculate the authentic mask from a pre-trained mask estimation networks. And furthermore, similar to the strategy used in the first stage, we will only use the useful and correct information of pseudos. And if we use the depth-based warping of the source view to a large angle, and there will exist many holes in the pseudos. These pseudos we cannot use directly, therefore we only select the faces of pseudos in the red bounding box. This is dependent on the input yaw angles. Here we present our experiment results. On the left, we show the quantitative comparison on celebrate AHQ. We can find that we achieve a higher reconstruction performance on the original view on both MSE, LPIPS, ID, pose, and depth. So, on the right, we show the comparison of identity preservation in normal views. We can find that other methods were degraded when the input face is a side face, while our method performs robustly and consistently as no matter what the angle the input face is. Therefore, we can find that the quality of the reconstruction has improved somewhat, and the stability of the reconstruction relative to the input view has improved substantially. Here we show several visual results. We can find that even if we input a side face to our model, the geometry remains correctly and stably. The symmetry prior introduced in our methods significantly improve the geometric correctness. And here we show the results of the ablation study and the multi-view dataset. Since our methods are incorporated with the pre-trained 3D GAN, our methods can editing the 3D portrait. Here we present several editing methods, including the text editing and the stylization. Thanks for watching, and thanks for your time.